Okay, we have a live stream, slides, we have an attendance code. I think we're good to go. We're just missing part of the audience, it seems. Should we wait a few more minutes? I didn't check if there were questions that I didn't get to. Right, okay, there was a question about the live stream. I guess that will be fine by now. I started it a minute after the question, so yeah. Yeah, again, apologies for being a bit later than usual. On the other hand, Friday, we always start a few minutes late. So I guess overall, I was later in the room, but not necessarily so much later to start with the actual content. Let's start with a bit of recap. I make that a bit longer again so that we have it fresh in memory. Okay, all the way back to the definition. I wanted to show this slide again. Yesterday we covered a lot of applications of suffix trees, and then I finished with, okay, that's all great, but they have these large constant factors, especially in the space overhead. And also the construction algorithms for suffix trees are tricky. So can we get the same, but do it simpler? And a first attempt to do that was to look at just this array of numbers, the suffix array. And the connection to the suffix tree was you get the suffix array by just reading the indices of the leaves in this alphabetic order, which is what you get if you read the tree left to right or top to bottom in this case. When you order at every node, you order the edges alphabetically. We've seen that that's good enough to do string matching with a little bit of a slowdown, but still fine. The tricky bit is how to compute the suffix array. Now, to be clear, we've totally lied away that issue for suffix trees. I just told you on this slide, oh, there's this magic black box. Believe me, for now, it's doable, but I haven't told you how to do it. And indeed, that's the tricky bit for suffix trees. So for suffix arrays, it's a little less tricky, and we'll look into it. And we've seen a simple solution last time already. Just starting the recap, so if you're joining now, it's fine. A simple way, because the definition is just the sorted suffixes, we can use any sorting algorithm. That's not so fast, but at least it's easy to code. And this is pessimistic. Like in the worst case, this sorting algorithm is not good. If you pick some actual text with English prose and apply this sorting algorithm, it would probably do reasonably fine. I've tried this once with some examples, and is fast enough even for large texts. But you can attack it in some sense with the worst case. We had the connection to the BWT. That was just to answer a question we left open in Unit 5. We didn't actually talk about how to compute the BWT quickly in that chapter. That was kind of left open, and it will come down to the same thing, sorting the suffixes. And then we had this long example. Let me zoom through that a bit quicker. If you don't want to implement a complicated algorithm, that's the one that's probably the closest to usable in most cases. It doesn't work for some extreme texts and still has a quadratic worst case for suffix sorting. But for many texts, this gives reasonable performance. And for sorting strings in general, that's about the most versatile and best method. So for details, I referred you there. What was still left open, like even if you're lucky with this quicksort-based approach, you never get below n log n for sorting if you use that method. even if your text is fairly friendly. I guess never is not quite true, but I guess it is true. Even if your text consists of a single symbol and they're all different, then you're back to sorting numbers and you're doing it comparison based. So we've seen a lower bound for n log n. So you won't beat this with this algorithm. But we can do better. And that's what we're here for. So long recap. And just for anyone who was late, here's the attendance code. Okay. In the next section, we'll look at a linear time, worst case linear time algorithm for suffix sorting. And I want to hype it up a bit again, or make you aware of it. It's the most complicated algorithm we'll see in this module, but it's very nice that each individual step is not complicated. It's one of those cases where coming up with this idea in the first place was really tricky, or it took people a long while. It's also one of the newest results we're seeing. This was published in 2000. I know some of the authors personally. This is all not that long and old, decades old results. This is closer to cutting edge research, but still very elementary in each individual step. But the algorithm accomplishes this feat that we somehow avoided so far. You have to somehow take a leap to do this in linear time. And maybe by the end of it, you'll say, hold on, where actually was the magic step that made this do something that people first believed wasn't possible? And I guess there will not be such a step. Every single step makes sense and is totally understandable. Anyways, it'll take us through today to get there. So let's start with a bit of an overview first. To make this algorithm clear, I have to introduce a helper definition, just because it's more convenient to formulate the algorithm for that helper result instead of the suffix array itself. So remember, L stands for leaves, because the suffix array really is the leaves of the suffix tree and sorted in left to right order. And what we'll introduce is the inverse suffix array. And it's essentially all that you need for the definition formally is in this line. It's the array that stores the inverse permutation. I didn't mention this so far. The suffix array always stores a permutation of the numbers 0 up to n. Just because the leaves in the suffix array are numbered by the starting indices, these are from 0 up to n. And the leaves come in some order, so it's some permutation. There's no duplicate numbers and there's no missing numbers. That's what that's supposed to mean. And this array R, the inverse suffix array, just stores the inverse permutation, which means if the rth entry in the L array is I, then the ith entry in the R array is R, with small and capital R's. Another way to express this, so remember from the definition of suffix array, this meant that if you look at the suffix starting at position I, then there's R suffixes that come earlier in the alphabetic order. Another way to say the same thing is Ti has rank R, starting at 0. That's how we defined it. And so you can interpret this R as the rank of a suffix. So here you give me the rank. In the leaf array, you tell me the index is the rank, the how manyth in sorted order do you want? And I'll tell you where it starts. For the R array, you tell me where the suffix starts, and I'll tell you its rank. Okay, it's the inverse of the two things. There's another way to memorize L and R. It's convenient that it comes down to the same convention, same letters. That's this picture here. And if you're more graphically inclined, maybe that's easier to keep in memory. And we'll use this picture a few times. So let me go through what it shows. We have our text. Then here, that just shows all the suffixes nicely aligned. So we have the suffix that starts at 0, 1, 2, all the way up through the last position. And there's nothing happened, right? This is trivial to produce. You just leave one more letter off at each point. Now, there's the R array showing here, which is for each suffix, it tells you its rank in the sorted order. On the right-hand side are the same suffixes, but this time sorted alphabetically. That's what suffix sorting produces. Then that also matches the leaf array, the suffix array, because these suffixes will appear in the suffix tree. The leaves will appear in that order. So here we have ordered the suffixes by their rank, the first, second, and so we're zeroth. If we start with 0. The 0th suffix is always just the $, because we defined that to be smaller than anything, and so on. And so the second meaning for these L and R could be R takes you to the right and L takes you to the left. If you know where your suffix starts, say I want this one, I know it starts at index 1, then R takes you to the right. It tells you you find it on the right at position 4. So you would go over here, and indeed there you find Anaban again, and vice versa. Okay? So this is not a complicated definition. I droned on about it for a bit because I want you to memorize it well, because we'll work back and forth between those two. It turns out that these algorithms to compute the suffix array are more conveniently formulated to compute R instead of L. But if you have this relation, you can compute one from the other quickly. So that's a simple for loop where you iterate through the positions and then you access the array with the result. So maybe a nice exercise to program that. But that takes linear time and is a simple, quick algorithm. So if we can compute R in linear time, we can compute L from it whenever we need it. To make double sure that you remember this stuff, let's go through some corner cases again. So this is not really a trick question. It is just double checking that the terms are clear. Okay, we had a phenomenal 88 votes for the attendance code. Let's see how many answers we get for this one. So about these options, L or R stands for, it doesn't need to be exclusive. Like they don't exclude each other. Okay, let's wait till 50. Oh, okay, there we are. Not much waiting needed. It's again a lot of answers, so In this case, almost all are correct. Let's just quickly go through them. So first of all, a few things are essentially just the definition. The suffix array lists the leaves of the suffix tree in left to right order. That is correct. That's one way to define it. So R does not have any direct relation with that order. It's the inverse permutation, so this is not true. It sounds like left and right, so be careful, but that would mean R is the mirror image of L, right? If you would swap everything around. That might also be useful. It turns out not to be useful here, so R is just something else. R lists the starting indices of suffixes in lexicographic order. That's the other way around. That's what L does, as you see below. That was the definition of the relation between the two, so not much more to say about that. And the mnemonics, I didn't want to throw anything in to confuse you, so these are all correct. You can take L to stand for the leaf array or for going left in that picture from earlier. And R can be the rank array or going right. So if you keep in mind that these are the directions of where we go, then that's the way to memorize it. Okay. So time for the actual algorithm. We'll go through in stages. So this is the high-level overview first. The algorithm is called DC3 or SKU. It stands for difference cover because you can generalize the algorithm, but that's not relevant for us. It does something fairly peculiar. So first of all, it recursively computes a part of the answer, namely all the ranks that start at indices that are not a multiple of 3. All right, so we have indices 0, 1, 2, 3, blah, 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 and those that start at 0 and at 3 and at 6, these are excluded, but all the others we compute recursively. So 2/3 of the answer is computed recursively. Okay, let's suppose that works. We'll use that recursively computed part of the answer to induce, so to derive from that, the other ranks. So the relative order of those that start at positions a multiple of 3. What I should say about these ranks, so this R12 and R3, these are only ranking relatively within their set of indices. So R12 tells you among all those that don't start at a multiple of 3, which is the first, second, third, and so on, it doesn't put this in relation to the total set of all suffixes. And similarly for R3. Of course, the final answer that we want is, in a way, the combination of these two, where we can, for every pair of indices, say which one comes earlier. Or we can determine the rank for every index in the entire set. And it turns out that you can do this with a merging step, which is not too dissimilar from the merge sort algorithm that we've had. But it will have a few extra tweaks to it. So that's the high-level thing. Solve 2/3 of the problem recursively. For the other third, we'll use a trick to get them cheaply from that. And then the overall result we also get cheaply from these two things. Now, let's first suppose all of that is done and solved. Why does that give us the required time? It's similar to what we've seen about the selection problem, finding an element by rank. There we had this, I was drawing this picture where you have 1, then you have 1/2, then you have a quarter, then you have an 1/8, and so on. So you have always enough. Maybe you remember this snake picture. That's a geometric sum. We have something similar here. If we assume that this step and this step takes linear time, the second and third step, then we by and large spend linear time on the first recursive call, the topmost one, for doing this these two steps. But we recursively have their same cost in the recursive call on the first part, but only on 2/3 of the input. And so if you keep going like this, you always have a factor of 2/3. You can upper bound this by going all the way to infinity with that sum. And that sum turns out to be 3. So you upper bound the overall cost by 3 times the cost of these two steps, assuming that they take linear time in their input size, which is, I mean, we'll have to show how to do that. But if we can show that they're in linear time, then the overall algorithm also just takes linear time. So that's the easy part. The rest of the time we'll spend arguing how we can do this. And note that all the formulation here is for R. As I said before, it turns out to be more convenient to compute the rank array instead of the leaf array, but we can compute the suffix array from R when we're done. The first step is just recursing. So in a way, that's not the hardest part. Let's look at the second step. So the second step, again, remember, we've computed this R12, and now we want to get R3 out of it. So R12 is known. For every suffix whose starting index is among those numbers, not a multiple of 3, we know the rank. And we can, by comparing the ranks, we can in constant time decide which of these two suffixes comes earlier in alphabetic order. Now, for all the others, we don't know anything so far. And our task is you can reformulate the task to sort these suffixes in linear time. If we have their sorted order, if they're in a list in sorted order, we can produce the rank array from that by just iterating through. The thing that occurs first gets the rank 0, the second gets the rank 1, what's at position I gets rank I. So it's a sorting task, but a strange one because we have this weird extra information. Again, in general, you would not be able to sort in linear time under these circumstances. It's not one of those cases. It's only possible because we have this extra information. So suppose we would like to compare two suffixes. So one that starts at 0 and then another one that starts at 3. We can't just go character by character because that would definitely be too expensive. In the worst case, if the text is really strange, it could take linear time. But if I chop off the first character, then I have something that starts at position 1 and at position 4 in this case. And now, while 0 and 3 were multiples of 3, if I remove one thing, and so I increase the index by 1, that's not a multiple of 3 anymore. For sure not. So I can take T1 and T4, and those two I can compare in constant time because I can use their ranks from this R12 array. So I can actually use this to do comparisons in constant time. If I want to figure out whether T0 or T3 comes earlier in the alphabetic order, I explicitly compare the first character. Now, if that one's different, I already know which comes earlier, whatever character is earlier in the alphabet. But if they're the same, then I instead look at the suffixes that remain after that. And those two, I have already all information I need for that. So in a way, you can rewrite this. Instead of comparing the whole suffixes, you take the first character and then the rank of the remaining suffix. So you formulate these pairs. These are pairs of one character and one number. So those can be ordered in constant time. OK, that's the first trick. And to turn that into a sorting algorithm, all you really need is the counting sort algorithm from back then in Unit 3. So here's a concrete example that shows that, how that works. So we have a slightly longer text. And to make life convenient, we're chopping off parts, multiples of 3. So it's convenient to add a few more dollars at the end to make sure that we always have enough characters to compare. Here are the suffixes that we would like to sort now. That's the ones that start at multiples of 3. And here are all the others, which we have recursively sorted. So here they are in sorted order. And here's their rank array. I don't know if it's big enough to read, but you can check at the slides if you want. Now, taking, I don't know if that's visible here. I've separated the first character of those suffixes. So if you take the first character and copy that down as a column, and all the rest of the suffixes you replace by the rank. So for example, here, Banana Bands, Banana Man, Bananas Man. So if I chop off H, I only have Anna Bands, Bananas Man. And Anna Bands, Bananas Man is here. It has rank 5. So that's why we get the 5 over here. That's the forming those pairs that I mentioned on the previous slide. And just visually, you see now, instead of sorting these long strings, you have these much smaller objects. And we can use radix sort, which means 2 rounds of counting sort. I can first sort by the first character with 1 round of counting sort, and then the second round among all those with the same character, I sort by the numbers. That's one way to do it. And then you get all of these in sorted order. And from that, you can just read off the ranks. Right, this one, T21, gets rank 0. 18 is the next, it gets rank 1, and so on. Okay? And that's the result of this step. That's R0. It's the ranks of everything that starts at multiples of 3. And we overall take linear time for this, just because each of those steps, constructing that list, takes linear time by just accessing the rank array that we got from the recursion. And the 2 rounds of counting sort take linear time. So it's overall linear time so far. Let's now have a look at the third step. We have, at this point, we have T0. And we have T12. So we know the relative order of all the suffixes that either start with multiples of 3 or not with multiples of 3. So these are like 2 sorted runs. You have a sorted list of strings, and you have another sorted list of strings. So in a way, what we can do is apply the standard merging algorithm from merge sort. And indeed, we'll do exactly that algorithm. What we need is a trick to speed up comparisons again. What would not work is, at each point, I have to decide which one is smaller, the single dollar or the $2. For those short strings, fine, it's a single dollar. But if you compare some long string, what you cannot do is go through character by character. That would give you a linear time for just one comparison. But we'll have to speed things up. Let's see. We saw a trick just before by splitting off the first character. And let's see how far that gets us. So let's suppose we have started the merging. So let's briefly simulate that. So we start at the first position. I'll take the smaller of the 2. That's this one. Put it to the output. Then I move 1 position down. This time this one wins. $2 is smaller than $3. Then this time that one wins. $1 is earlier than any other character. And now things start to get a little more interesting. Both starts with an A, but then H comes before N. So move that one down. And now we move this one out because A and dollar comes before A and A. So I sketched how you would do the character by character wise comparison, just to get us to this point. But this is not what the algorithm would do. So the next step is to compare these two. It's a general situation where you could have some long strings. So let's try the same trick that worked for step 2. This is one from the green run. This is one from the blue run. If I remove the first character, what's left is some suffix from the blue group. So it's A followed by T16. If I do that with 11, it's also A followed by T12. But somehow the trick failed us in this case, because what we started with was 2 suffixes from opposite colors. And by removing a character, we got 2 new suffixes. They swapped roles, but they're still from opposite colors. So it didn't work in this case. But if you go one step further, if you remove a second character, then it always works. So in this case, if you take 16 and 12, and you chop off one more character on either side, you're guaranteed to get 2 blue ones. And this works in general, because think about a general situation. So I have my 2 suffixes. I don't know exactly where they start, but they always have this pattern: 1 green character and then 2 blue. In the sense of, I'm coloring characters. If you start the suffix at this position, you would get a suffix of that color. Right, so this is a multiple of 3. And these two are not a multiple of 3. So if you just write the indices in modulo 3, you always get a 0, 1, 2, and the 1 and 2 are blue, and the 0 is green. Now there's different options how things could align, but suppose this one starts with green and then 2 blue. So I have green and blue. I cannot compare them directly, but if I remove one character, I have blue here and green here. Still doesn't work, as in this case. If I remove another character, then I'm back to both blue. The other option that you could have had was would have been here 2 blues. And in this case, one step is enough. If I remove the green here and the first blue, then I have 2 blues. And that's the only 2 cases you can have. You start with 2 opposite colors, so that one has to start with green. And then the one that starts with blue, it could either be a 1 or a 2 modulo 3 that you start with. And in both cases, either you remove 1 character or you remove 2 characters. After that, you have 2 suffixes that are both from the blue group. And so you know how to compare them. So what the outcome here is, I can use R12 to resolve any comparison after checking 1 or 2 characters up front. And so I can do every comparison in constant time. So maybe let me spell that out. So by checking whether your starting index of the 1 is modulo 3 a 1 or a 2, you can determine whether you have to check 1 or 2 characters. And if they're the same, then you have to compare what R12 gives you, but then you've resolved the comparison. If every comparison takes constant time, then the overall merging algorithm takes time linear in the size of the output. That's the same analysis as we've looked at in Unit 3. So with that, we could actually do the merging in linear time too. At this point, it feels like we've solved step 2 and step 3, both in linear time, so we should be done. Unfortunately, there's a little thing I glossed over. So for the overall algorithm, we have to pay a little bit of attention to step 1 again. So what we've done so far is step 2 and step 3 can indeed be done in worst case linear time. So in step 1, all we should really need is recurse. But if you look closely at what we've done there, I cheated a bit. In this first step, I said, let's recurse on all the ranks that are not a multiple of 3. But I can't just take an arbitrary subset of indices and claim that's again a problem of the same form. The overall problem was, here's a string, sort its suffixes, or more specifically, here's a string, give me the rank array that tells me for each suffix its rank. That was the original problem. That's what we're solving. But now I'm trying to call the algorithm recursively on, here's a string, take all the indices not a multiple of 3 and sort those. That's not quite the same. To do that recursively, we would need a string, some string t prime, that if I call the problem recursively on that string, would give me exactly the ranks I need. So we need a string that somehow skips suffixes. If that sounds odd, I mean, you need to modify the string to make that work. And luckily, there's a relatively simple trick to make that work. Instead of taking the original alphabet, we form triplets of characters. We've seen that kind of notation before in the compression unit. So all that means is I'm blowing up my alphabet. Instead of having all the letters that I had before, I now have all triples of possible characters in principle. And I'm transforming my string by grouping characters in these triples. So if my original string was this, my new string t box is always 3 characters boxed together. So in particular, I would write that the length of t box, the number of characters here, is just 4, right? There's 4 boxes. That there's stuff inside the box is kind of hidden in the definition of the alphabet. Now the main trick is if you take the suffixes of t box, these are exactly the suffixes that start at 0, 3, 6, 9, so on. All the suffixes that start at multiples of 3. Okay, that's kind of the opposite of what we wanted. We wanted to have all those that don't start at a multiple of 3. But that you can get by just shifting things a bit around. So our actual t prime is not t box, but it's leaving off the first character of t and making the boxing construction on that. Make some dollar boxes in between to make sure we separate things. And then you take the first 2 characters away from t and apply the boxing construction, and you append all that. And the result of that, I'll show you an example on the next slide. The result of that is that all the suffixes of this t prime are the suffixes of t that start not at a multiple of 3. There's a little bit of a sneaky trick, but by modifying the alphabet, you can indeed give the algorithm a different string on a different alphabet that looks quite different from the string you started with, but it solves the problem that you need to be solved. And then it's a proper recursion. Let me see if I can do. Okay, let me jump over this and first show the example, just briefly. So here's our original text, same as before. What I need is the first character chopped off. So I removed the h, and then in the second part, I removed the first 2 characters. And then I apply the boxing construction to those. Okay. And I was generous enough. If there's a box that has not enough characters, we'll just fill it up with dollars whenever needed. So that's the construction. That would be our T prime. Now, if you were quick enough to read, I again cheated a little bit, but again, we can fix it. So by this trick with boxing things up, we created a new problem. And the problem is that the alphabet size explodes now. If I start with 26 characters in the first step, some Latin alphabet, in the recursive call, I make triples of that. So that's 23 cubed. I don't even know from the top of my head what that is, but it's 1,000. It's more than 1,000, right? And if you go one step further, then you take 1,000 cubed. And that's 1 billion. And then one more step, you take 1 billion cubed, and then that's the end of the story, right? So it's exponential growth is not good, especially if it's cubed each time. That's even worse than well. It's pretty dire. So that wouldn't work. Now the solution is that well, the algorithmic way it breaks, apart from needing space to store those, the linear time sorting step doesn't work anymore. Remember, step 2 started out with taking the suffixes of just take the first character, then append the rank, and then sort that. And we said, that can be done in linear time with counting sort because that first column is just a single character. But now my characters are actually blown up triples of triples of triples of characters, so they're entire long strings. And so the whole linear time sorting breaks apart at that point. Okay. Now, of course, our actual string doesn't really get bigger. So if we had this 24 characters in the original string, we don't magically make up new characters. And in particular, because this T prime has roughly length 2/3 of n in numbers of characters, there can be at most so many different triples that occur in that string. There's just not enough space to have all of those the triples that are possible. So instead of using these nice boxes that I've drawn for you, we replace those by numbers. And for that, this is called an alphabet reduction or rank reduction. So what we do is we sort all the triples that actually occur in our string and replace them by their rank. So we compress the alphabet down to all the characters that really occur in the string, as opposed to having space for all possible triples. Now that sorting step can be done in linear time by 3 rounds of counting sort, so no cheating involved here. And this means that the alphabet size never grows beyond the length of the string. We never have a character that doesn't occur, so we never have more than n characters. So let's do that on the example. Here's the triplet representation. The triples that actually occur in that string are almost the same. There's just one that's repeated. But that is because the example is fairly small and has a large alphabet. If you have a longer text, then necessarily you will have many more triplets that are repeated. But here's all that occur. We sort those. So in alphabetic order, they're listed here, and they all have a rank. And this is the very same trick we've had before in disguise. And so we replace every triplet by its rank. And again, you should treat this as one number, not as a string of decimal digits, but in the standard way, an array of numbers. So the real string we recurse on is T double prime, which is obtained from this boxing construction and then replace every character by its rank. And with that, indeed, all the cheats have been resolved. We've reduced it to a proper recursion. It is now exactly the same problem we had before, a single string over a reasonably sized alphabet. So recursively, the same running times hold. And the rest of the algorithm is as I showed you. So to discuss what we've achieved, we found that we can compute this suffix array in linear time, and the algorithm is a bit intricate, but it's actually very little code. If you code this up, it's not much. You need some counting sort, and you need a little bit of operations to produce these triples, but it's all just arrays and sorting. Both can be in little code and fast in practice. If you don't want to go that far, the fat pivot string quicksort is also relatively quick for many arrays, for many texts, and is much easier to code. And we can use this to do string text indexing or string matching in a very good time, just logarithmic in the length of the text, only slightly slower than what the suffix trees gave us. But it is slower, so at least from a theoretical perspective, you might not be 100% happy yet. And what's more, there's a lot of things. I tried to show you different applications of suffix trees to prove their versatility. They can be used for many different string problems. And so far, we can't really use that full power. So far, that's a disadvantage of using suffix arrays. OK, time for our little break. So I want to stress that we've seen the full thing for computing the suffix array. I haven't really shown you how to compute the suffix tree, right? So that black box is kind of still up there. But the most complicated part you survived. So that was the toughest algorithm we covered. Hey, question?
I just don't know how to compute the for example, this one. Or I don't know what it means that TI has rank R.
It means what's in the line above. So rank R means there's R things that are smaller. So for example, let's take A-ban, which has rank 1. Yeah, it should be first, not 1th, but anyways. So among all those strings, there should be exactly one that's smaller in alphabetic order. And you can read this off immediately from this one. There's A-ban here, so there's one smaller, which is just the $. That's why it has rank 1. So the rank is the position in the sorted list. That's all.
Before TI in sorted order.
Yep.
So TI means AD.
TI, so I is the starting position of the suffix. So here would be 5 because you're leaving off the first, whatever, 6 characters.
This one?
Yeah.
And TI is A. And there are suffixes.
So the notation T sub I is the entire suffix starting from position I and going until the end. And the A is just the character at position I, right? You have to tell those two apart if you say it. So T square bracket I would be the single character at position I. That's A. And T sub I is A-ban $. So is it clear what I mean, the difference?
Maybe I should. TI is a suffix tree. Suffixes. Suffix tree. In a tree.
No. TI. TI is the suffix.
It's
one string. No, TI is a string. That's the suffix starting at position I. So we wrote this as, we wrote it. Sorry. TI is TI dot N. That's the way I wrote it earlier, but then it occurs so often that I wanted something shorter.
So in this one?
Yeah, so T5 is A band dollar.
T5 is $8M.
Mm-hmm.
And Y R.
So R of 5 is 1 in this case.
First 1 in this case. And why?
So it's 1 because there's supposed to be one of all the suffixes that are smaller in the alphabet than T5.
Smaller?
Yeah, earlier in the alphabet.
Even the number?
No, as a string. Right, so here's all the strings, and they are in sorted order.
Come before TI, so there are suffixes.
In, lexicographic order.
Before TI.
Smaller in lexicographic order, that's what it should say.
Is the number? This one? EAMAM.
Now that's not a suffix, right? The suffixes has to go until the end of the string. So these are all the suffixes. These are all the suffixes of our text, banana Ben. And you get those by removing one more character in each step. Now you can take those strings and sort them. And what you get is this order. And then, the rank is just the position here. So A-ban is at index 1. That's why it has rank 1.
I can understand this one, this part, but I just cannot understand how to compute.
Well, I mean, just use that formula then. I mean, it's nothing really complicated. Maybe the terms are just more confusing than helpful. Right, so if you figure out this one, that L1 is 5, that's all you need to know to put R of 5 to 1.
It's like a mirror.
It's just inverting the numbers.
Thank you.
Okay. There are a bunch of questions on Slido, but I'll do that part first. I think we'll not need the full time probably for this. Then we can cover the questions after that. But I think we should conclude that section. Then we're a bit ahead of time. We have more time for exam recap next week. I think that's useful. So we have one more thing to do. In a way, it's two things in one go. We haven't seen how to do all the fancy applications of suffix trees if you just use the suffix array and forget about the tree. And I kind of promised you an algorithm to compute the suffix tree, at least just for the theoretical part. It would be nice to clear off that black box, and we haven't done that either. It turns out that you can do these two things by the same solution. In the last section, we'll look at the LCP array, which will turn out to be the solution to both applying the suffix array in the same examples we've seen for suffix trees, and to finally clear this black box of how to compute the suffix tree, the full one, in linear time. So far, we've only done that for the suffix array. And to motivate that, let me remind you or ask you to remember what we needed for the first of these more interesting applications, which was finding the longest repeated substring in a string. So again, this was find some substring in the text that occurs in at least 2 positions. It's fine if these are overlapping occurrences. We could solve that in linear time using suffix trees. And we used some features of the tree there. And that will guide us towards what's still missing if we just have the suffix array. There's really just one answer that's definitely needed. Let's get at least up to 50 again. Unless we never get there. Yeah, I think it fizzled out a bit, so there's been votes for most answers, but the majority is on the right track. So if you just remember from from yesterday, basically, the key feature that we needed was the string depth of internal nodes. We needed the internal nodes to iterate through in particular. So just as a reminder, the algorithm was very simple. If you have the suffix tree available, you compute the string depths of the nodes, or you remember that it's actually a compact trie and you have the string depths anyways. And then you find one of the internal nodes of maximal depth, maximal string depth, and read off the path from the root to that node. So in our example, we found that there's 2 solutions here. The deepest are tied for these 2. It's either Ben or Anna. Both is the longest repeated substring. It doesn't necessarily have to be unique. So if we just have a suffix array, it might be not so clear how to do that. But we can indeed add a second array, and then it becomes possible. That will be the LCP array, the longest common prefix array. It's a term that we've had already on the slides back then. It stood for taking any 2 suffixes, give me the longest common prefix, the longest common part that they share. But it turns out that's too much. If I can take every pair of leaves, that would be quadratic in size, so we don't even have the time to write that down. But we can strip it off to only look at adjacent leaves in the sorted order. So the key definition here is this one. The rth entry in this LCP array is taking the leaf, the rth leaf, leaf of rank r, and leaf of rank r minus 1, and compute their longest common prefix. So in a way, what we have is we have those leaves here in that order. That's the leaf array, the suffix array. Right? It has 9, 5, 7, 3, and so on in that order, if you check with the example from before. And the LCP array has for adjacent pairs in here a number, namely the string depth of their longest common, so the string depth of their lowest common ancestor in the tree. So here it would be 0. Here it would be the lowest common ancestor is this node, so it would be 1. For these two, it would be 2, because that leads to that node where these branch off. The lowest common ancestor of those two is this, which is 3, and so on and so forth. Here we go back to 0, then we have another 3 here. Nobody can read that. Another 3. Maybe I should, this could be mistaken for zeros, I guess. I'm just trying to show what leaves they correspond to. Here we have another 0 because the lowest common ancestor is the root. Here we have 1, and here we have another 2. So if I straighten this out, the leaf array would be 9, 5, 7, 3, 1, 6, 0, 8, 4, 2. That's L. And, you know, the indices would be like this. And the LCP array, you should really imagine it sitting between those numbers. So it should sit here 0, 1, 2, 3, 0, 3, 0, 1, 2. Unfortunately, we can't really tell most programming languages that we want this to have index 1.5 and this index 0.5 and 1.5 and so on. So instead it's shifted. So this is index 1, 2, 3, and so on. So it starts with 1 here. Unlike most of our arrays, we don't use the 0 entry for this one. So that is LCP. Okay, that's from this example. That's what you should imagine here. Now for the longest common substring problem, all we need to do is find the largest entry in the LCP array. And we find indeed there's 2 times the 3. So that's the length of the longest common, of the longest repeated substring. And if we want to know what string that is, we have to check at what indices that occurs. And that gives us the two suffixes that start with that thing. So here's that connection drawn a bit nicer again. That's the leaf array. That's the suffixes that it corresponds to. Here are the longest shared prefixes, the longest common prefix between any adjacent 2 suffixes. Nothing for these 2 because they differ on the first character already. And for some others, there's a longer common prefix, up to 3 characters here. That's why the LCP array looks like this. Now, you can draw the same information slightly differently as intervals, because it turns out the things that are shared, so it's not just these numbers go up and down. Also, if you look at the part that is shared, A, AN, A, they all share an A at the beginning. So you can say there's an interval among the sorted list of suffixes where they all start with an A. And nested within that interval is one where they all start with AN. And so on and so forth. Sometimes these are just a single a single pair of suffixes, sometimes there are more. And here comes the cool trick. So that's the part to pay attention to. These LCP intervals correspond one-to-one to the nodes of a suffix tree. So again, if I have the suffix tree, every internal node corresponds to such an LCP interval. So a range in the sorted list of suffixes and a prefix that everything in that range shares. The root corresponds to this dummy shared prefix of the empty string that everyone starts with nothing. Okay, fine, that's kind of a corner case, so that everything is covered by one interval. Then the children of the root, there's one that goes to A. That's this range. That's the LCP interval where everything starts with an A. And this holds true in the other direction. There's nothing that only starts with B. The whole thing is contained, so everything that starts with a B actually starts with BAN. That's why there's an internal node for the prefix BAN, but nothing in between. There's no other internal nodes before that. So it's really a one-to-one correspondence, and that might help you appreciate that from just the LCP array and the suffix array, you can reconstruct everything that's in the tree. All the information is in there. It might be a little bit hidden, or it might be a little opaque to see it, but the key information is there. And so you can indeed reconstruct the tree with a simple algorithm from those two arrays. We don't do the full code, but you'll do an example in the tutorials to practice it a bit. In a way, you can do it like this. You align the suffixes in sorted order, and if you have the longest common prefixes, it's easy to also determine these intervals. It's just ranges where there's the same minimal number. So this A corresponds to a range where the LCP does not drop below 1. But there is one occurrence of that number. And from that, you can reconstruct the suffix tree. What I want to show you here as the last bit is, where does this LCP array come from? I've introduced yet another array, so we need an algorithm to compute it. And again, it should be in linear time to be interesting. So the last section will be about constructing the LCP array efficiently. You can go by the definition and compute it naively. Often that's not very slow, but in the worst case, it takes linear time for each entry, so quadratic overall. Again, a possible worst case is the degenerate text of all A's, where you have these long shared suffixes all the time. The insight to speed that up is if you imagine doing this naive algorithm for every next pair of leaves, you start comparing from the beginning how many characters are there the same. Suppose you do that and you have one really long entry. For example, here you have this valid, grammatically correct English sentence of buffalo, 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 buffalo. And you can add more buffaloes to this. If you haven't seen this, a fun one, but it's a bit beside my point. If that's your text, then you may have these two suffixes in sorted order that share a long shared prefix. Whenever you have this, we actually are guaranteed to find more large values, and we can kind of deduce those. Let me show that on an example, and then we'll do the proper algorithm. So suppose you have a first few of these of suffixes of this text in sorted order, and you found a really long common prefix between those two. Well, if I take off the first character of those two, then they become two other suffixes, but they still share a lot because it's just one character less. If they were the same for the first 18 characters, then chopping off that first character means they share 19 characters. They still share 18. The tricky bit is just to find where does that 18 go. We know there's two suffixes that have a longest common prefix of 18, but which ones? And what's more, it may not be that these are adjacent, and then they don't actually have an entry. There might not be an 18 anywhere in the LCP array, because these two are not adjacent in sorted order. That's the slight caveat. But otherwise, this is the key idea. If you have one longest common prefix between two suffixes, then there must be many other shorter suffixes that all lead up to this long shared prefix. And so you can capitalize on that and amortize the cost. And that's what Kasai et al.'s algorithm does. The trick is to compute the LCP entries, the values in the LCP array, in a smart order. And it turns out the smart order is not going from beginning to the end of the LCP array, but to process the suffixes in the order of their length. So let me illustrate how this works on an example, and then we'll see the full code afterwards. So we start with the longest possible suffix, the entire text. Now we find where does this lie in the sorted order of suffixes. So we use our right to the right array, the rank array, to know the rank of this is 6. So I find it at position 6 in the sorted list. If I know that, I can go to position 5, the previous one. That's this one. And I can check how many characters do they share. Now this I do naively, so I go through the characters one after the other. They share these, they share this, but then it's done. Right? Then the shared prefix stops. So I determined one entry, one longest common prefix entry, namely 3 at position 6. Okay, now we're trying to make use of that information. And the way we do that is if we now go to the next suffix in the text order, the one that just loses the B, I'll try to find again, where does this occur in the sorted list? I use my rank array. So I go to 4 and I find the one that's before that in sorted order. And here comes the trick. Because there were 3 shared letters earlier, if I just remove this one B at the beginning, I have 2 matches, 2 characters that definitely are the same without checking. So I don't need to compare those 2 again. These are for free. And I start comparing one character after that. In this case, there's one more character, but then the 2 strings differ. So I have another entry of 3. But I only paid 1 comparison to get it. The other 2 were for free. And that's all. That it keeps going like this. That's the algorithm. So if you go to the next position, we check where do I find that in the sorted order. Well, it's at position 9. So we jump down here. Now we look at these 2 strings, and we know they had a length 3 shared prefix before. If I lose the first character, there's definitely 2 that are shared. And in this case, that's also where it stops. The next character differs. So I have an entry 2 to go into my LCP array. And I paid a single comparison again. And we keep going the same way. In each case, we take the entry that we wrote into the LCP array last time, subtract 1, because we removed 1 character. And that's the number of characters we definitely have a match for. And the others we just naively check. For this one, we go over here. We know 1 character is inherited, 1 match. There's actually 1 more that we pay for. And then we get an entry of 2. We go to the next one, find where it is. We have 1 inherited match. That's the only one, so we leave it at that. So for the next example here, we don't have any inherited matches because 1 minus 1 is 0. And here indeed, the first character already differs, so we get a 0. And the same thing happens here again. And then for this one, we don't have any inherited matches, but we find by comparing that there's one character that matches. And that's all. If you write that down as an algorithm, it looks like this. We need the suffix array and the inverse suffix array to be computed already. We need that to go back and forth between those two left and right pictures. We need the rank array to go from a suffix here to its location in the sorted list. But then we also need the suffix array to go from position 7, position 6. Where does that guy start? I need to know where I have to compare. So I need both L and R. These are computed up front, and we know how to do that from the sections before from today. L remembers my, my match that I found so far. And then I go through all the suffixes in text order. I look where it is on the right-hand side. That's my to the right array. I take the suffix above me and find where that is in where that starts in the text. And then I do my naive check, but I start with these L matches that I inherited. So those I don't check. I start at I plus L and I minus 1 plus L, and keep increasing that as long as there's a match. Then I store my the prefix I found in the LCP array. And then for the next round, I remove one character, so L gets one smaller for the next round. It's fairly short code. It does exactly what I've shown you in the example. It's just a little, getting all the indices in your head is a bit confusing. I always prefer the example and then derive the code from that. Let's briefly analyze that algorithm because, yeah. They skipped the fire alarm last week, I think. I was hoping they might also delay it, but no, there we are. Okay, let's quickly analyze the algorithm because in a way it looks dangerous. It has this inner loop and it has an outer loop. So can we guarantee that it doesn't go quadratic? And the reason, again, similar to some string matching algorithms we've seen, is we can do an amortized analysis. We can separately count how often this comparison comes out as equal or as not equal. The not equals are easy because whenever I have a not equal, I skip this inner loop, so I can only have one mismatch for each outer loop iteration. So there's at most n such comparisons where the outcome is not equal. And for all the ones where I have the equal outcome, I increment L afterwards. But L is never bigger than n, and we always make it one smaller. So it's only make it one smaller at most. And so if I add this up, I have at most 2n comparisons that I spend where the outcome is equal. It's similar to KMP and some of these algorithms. It's kind of a potential or a bank account argument. We keep L from the round and we only adjust it slightly. So it can move up and down. But if it moves up a lot, then we profit from that for many future iterations where we can't have another expensive operation. If one iteration of the outer loop made L move very far and spend a lot of time in this inner loop, then the next iteration cannot do the same. Okay, so overall, again, it's linear time because all the key operations only happen a linear number of times. With this, we can puzzle together our algorithm for suffix trees. Again, the details you will try in the tutorial. You compute the suffix array and then the LCP array, and you use this connection with LCP intervals to know exactly which internal nodes there are, and so you can reconstruct the tree from that. These two things, suffix array plus LCP array, is also called the enhanced suffix array, because the suffix array has been enhanced by the LCP array. But this really is a more general thing. It's a bit more tricky to reason about as compared to having the suffix tree explicitly. But it turns out you can simulate everything that you can do in the suffix tree. You can simulate based on these two arrays. With maybe extra tricks, but it's essentially just your mental load is higher in designing the algorithms. But there's an almost automatic translation. If you tell me how to do it on a suffix tree, you can translate how to do it using just the two arrays. They use much less space. They don't have a dependence on the alphabet in the sense that the suffix tree had. And we've seen two algorithms today to compute both arrays in linear time. And they're a bit more tricky than many of the things we've seen, but not too crazy. That brings me to the end of Unit 8 and also the end of the exam relevant material. There's one black box that we left in this unit, namely the one for finding the lowest common ancestors of two leaves in the suffix tree. And we'll come back to that next week in the bonus lecture. And I hope you enjoy that too. As I said, it's not part of the exam, but it's a nice way to clear off that box. Apart from that, that concludes the unit on text indexing. So we've seen ways, efficient pre-processing on the text, and then do all sorts of interesting queries on the text, and efficiently so. Let me go back to the questions on Slido. Okay, I should probably stop that one. Okay, past exams. Yeah, I remember writing to the student experience team about it, and I don't think I have a response. So maybe we'll ignore that and just do it internally. So I don't see a reason why we shouldn't share it on CampusWire. I didn't want to undermine their process, but if it's still not on Canvas, I'll double check after the lecture. You know, this all student Canvas course, and they announced that all the exams will pop up there. I answered this many times if it's about the class tests, 7 in total, and I think we can release the last one now. It was about material we hadn't covered yet. So the mock exam is on CampusWire. It's essentially a collection of previous exam questions. It's not comprehensive. No exam that I've ever posed covers all the things that we discussed in class and into tutorials. Exams are always spot checks and leave out some areas, but of course, the areas that they cover differ. So you have to, if you leave gaps, then it's your gamble. In principle, anything that we covered in class and in the tutorials can be asked in the exam, but any single exam will only pick a subset. So also the mock exam picks a somewhat arbitrary subset. So don't rely on things. If they don't appear in the mock exam, that doesn't mean they're not relevant. It's just take it as an example of what type of questions are asked, and don't obsess about the concrete example too much. It's more about having practice material for you. Many of the things in the exam are well suited to be prepared for. I mentioned earlier, so there's 3 types of questions. There's reproduction, there's application, and there's transfer questions. And they always come in this order, 1 each for each of the 5 sections, right? So it's very structured. The first part, there's no good excuse to not have the answer for the bookwork questions readily available. And remember, I think I said this, you're allowed to bring a cheat sheet for the exam. So I allow you 1 A4 page. You can use both pages, front and overleaf, but it has to be handwritten by you. So you can write small if you want to, but it should be handwritten. And you're allowed to bring that one sheet. I don't think there's anything that's not allowed to be on there, well, within the normal rounds of being decent and well, whatever. But there's no no forbidden material or so. The reason to restrict it, I'm not a big fan of letting people learn things by heart, but also it doesn't make sense if you bring books of material and spend the exam time flicking through your material instead of thinking. So restricting it to this one page forces you to think about it. And most of the time people bring that sheet and then don't look at it, but producing it helped you. Right, so bookwork questions are easy to prepare for. Because they cover existing things, so statements that we had in class or in the tutorials. The application questions are usually applying an algorithm on an example. We've done many examples in class. We've seen many algorithms. You can just generate random examples for yourself and practice to do those. And you can, in particular, also practice to do those quickly, right? So you don't lose a ton of time on doing the examples. That's also easy to prepare for. And with those two things, that's already 15 out of 25 marks for each section. The transfer part is harder to prepare for. That's why we've had a few more examples in the last tutorial sheet and on the mock exam. That require a little bit of extra thinking out of the box. So that just needs practice. And the exam is best 4 out of 5. So you have one shot where you just blank and it doesn't affect the mark at all. And for the transfer questions, that's often needed. Otherwise, it's not super fair. And the best way to prepare for them is to just do many of them in practice. Okay, we're jumping around between different things. Right, okay, misconception. The mock exam is just it's just a PDF, right? There's no, it's not an organized mock exam in that sense that we come into a room and practice the invigilation and so on. I don't think you need this, right? You've all done an undergrad, so you know what exams look like. Maybe they look a little different in Britain than where you did them. I mean, the important bits are be on time, make sure you turn off all devices, especially phones ringing during exams is not so much a problem for the others. But probably your attention after that will be, your focus will be destroyed. It happened last time, and it was not pleasant for the person. So try to avoid that. Turn everything off. Don't have alarms set on your phone in particular. Bring an ID. It's kind of the obvious stuff. There will be some general announcements about the organizational bits, I guess, together with the exam schedule released on next week, Tuesday, or what it was. Yeah, so the mock exam otherwise is just extra questions to practice. You don't need a calculator, or there's no calculator allowed. So any kind of actual calculations are designed so that you can do them by hand. But you've seen the module. How many times did we really do integrals or any fancy calculations? It doesn't occur much. The calculations you have to do are executing the algorithms that we discussed. And the calculator doesn't usually help much there. I'm not sure exactly what as a formula means here. So the exam can have different questions. I hope there's all different parts covered in the mock exam and on tutorial 10. I mean, there could be a question that shows, here's an algorithm, and it gives some pseudocode, and it asks you questions about that code. For example, well, someone claims this does X or Y. Do you think that's correct? Or, yeah, I've had questions. Someone shows you this code and is super excited about this feature. What do you think about it? That would be transfer questions, right? These are the tricky ones that need some thought. In that context, pseudocode is part of the exam. Yeah, some transfer questions are small algorithm design questions. So you're given a problem and you're asked to design an algorithm to solve it. then you can write pseudocode as part of the answer. But there you're kind of free. As long as I can understand what you mean, it's fine. It doesn't have to be a specific format. Or it can be Python code if you prefer. What else? Yeah, I don't know if you want to clarify what as a formula means. So the exam is on paper, right? You get a printed thing. There's no electronic devices allowed in the room, by and large. Okay. Okay, there's a few questions about the submission today, which I extended to 1 minute to midnight, British time. The impossibility result is an optional part. I decided against making it part of the marked assessment because it always was something students struggled with in the past. So in that sense, you can write as much as you want there. It's not a problem. If it's too long, it might not get read, but you don't harm yourself. I think it's very insightful for both problems, both programming puzzles, to think about impossibility results, mathematically proven statements that something is not possible. So in the context here, maybe you can prove that you can never achieve 21 correct questions, okay, out of 20. But maybe you can also argue you can't do 20 or even less. It's insightful to think about it, but it's optional, and so no marks for it. Good question. The text file. I think whatever the website says, I think it's just a number, just your claim what mark you achieve. And we'll have a look at the code, and if that looks dubious, we'll just run it again. But we don't want to run all the code of all people by default. That takes time. So you should do us the favor of putting the number there that we can quickly access it. But if you claim stuff that's not true, we'll usually have a good BS detector for that. Exactly, it's not marked, or at least it's, yeah, you don't get a mark for it. Yeah. Right. We'll do that next week. So it's not compulsory. It's up to you. I mean, I would ask you to do it because it always undermines the results from other people. If there's only 10% voting, you can't really convince anyone to change something. If only a 10% said, this would be better that way, maybe the 90% all disagree. If many people vote on the end of module survey, it gives the whole thing more credibility. But I'll leave time next week to fill it out. Okay, so there's no 9 previous exam papers. There's 1 mock exam with 9 questions. Is that where the 9 came from? Yeah. Okay. And I'll check about the exam from last year, the past paper that the student office promised. I'll put that on CanvasWire if it's not there yet. Oh, you asked about Canvas, not CampusWire. The all-student Canvas course. I showed it in the past, I think. So if you go to your courses, okay, it's a ton of my stuff, but this is the all-student course. And there's assessment-related information. I mean, you should know this Canvas course in and out. There's lots of important stuff. If this is the first time you hear about it, I'm a little concerned that you might have missed other things. Sorry, no, I was clicking the wrong thing. Past exam papers. Yada yada yada. Okay, coming soon, shortly after the exams, I guess. That's okay. I'll put it on CampusFire then. It makes sense to start prepping a bit ahead of time. Good. Anything else? Well, you know where to find me. So